Hey guys, it's Ms. Gephardt, and we're going to go through and talk about relative versus absolute age. So make sure you're kind of got something ready to jot down some notes. And again, as you go through this presentation, if you have any questions, do make sure you're writing those questions down so you can address them to your teacher. These are the essential questions. So if we walk out of this lesson and you can't answer these questions or you have no idea what they mean, you need to go back and you need to read them over the presentation over again. You also need to ask your teacher or come in for some help. So we're looking at, can we know the amount of parent material in a rock sample by using a half-life? Does the amount of material change as time increases, or how does it change as time increases? And then understanding how that relates to rock and fossil formations. All right, so the first thing we're going to start off with is something called relative age. Relative dating, I should say. And relative dating just means the order of events in relation to other events. So right down here, where my mark is, okay, that rock all the way down there is the oldest rock because it's on the bottom, and everything that's above this rock is getting progressively younger. So it's just relation. We don't know an exact amount of time, we just know that this is older and we get younger as we move up. So if you have an older brother or you have a younger brother, you wouldn't have to tell me your age. When you said I have an older brother or I have a younger brother, I could kind of figure out about where you fall in terms of your age. This is also known as something called the law of superposition. So the law of superposition states that the rock on the bottom is the oldest and it gets progressively younger as we go to the top. Doesn't give us any exact years, okay, for a fossil or a rock. It doesn't tell us exact, but it does tell us in relation to other layers. And this works best if we haven't folded or overturned. So basically, this works best when we have nice, pretty little lines like this. These rocks are just very nice and linear. Sometimes the earth, we get some of this bending and folding and stuff, and it makes it much harder to actually date the rocks. Absolute dating, this is the exact age. This is when we get it is X number of years old that the rock or fossil is. Mostly we're going to use this and see this in igneous rock, but metamorphic rock can also be dated this way. Sedimentary rock is not going to be dated this way. We're going to look at sedimentary rock in terms of relative age. So that's more what we're going to look for. And sort of using igneous rock and metamorphic rocks as an exact thing in comparison to where the sedimentary rock falls, we can kind of piece together exact times. Radioactive decay just means we're determining the absolute age of a rock or a fossil. So radioactive means there's elements on this planet that are radioactive, which means they break down or decay. And when we think of decay, I want you to think about a dead animal. It's really gross, but think about a dead animal. So if Skippy the squirrel comes skipping across the road and your mom's car does not stop in time, Skippy gets squished, okay? And so if we see Skippy and Skippy gets squished, we all feel sad for Skippy. If we come back in a week and we still look at, and Skippy's still there, Skippy's starting to look a little different. If we come back in a month, Skippy looks a lot different. He's decaying over time. The thing with radioactive elements is that they decay at a very specific rate in a very specific amount of time, okay? And all it means is that the atoms are just breaking down on the inside. And the one thing to know is that all of these radioactive elements have a certain rate. So I can't tell you one rate for all. They're all going to have their own. This is also known as something called half-life. And with half-life, it's how much time it takes for something to divide in half. And everything's different. All right, so if we look at carbon-14, carbon is found in all living things. And so when we meet our maker and die, okay, our carbon is going to be left and it breaks down. It's a radioactive element that will break down. It takes 5,730 years for it to break in half. So if I have 100 grams of carbon-14, after 5,730 years, I'm only going to have 50 grams. That's all I'm going to have left, okay? After another 5,730 years, how much do you think would be left? And then how much total time do you think would have passed? All right, so if we look, we're going to see that we would have 25 grams because we went one more time. And the total amount of time that's passed is 11,460 years because we have to keep adding those 5,730s together. All right, half-life, we're going to use it to date rocks or fossils. Oh, just kidding, sorry. We're going to use it to date rocks or fossils. And when we use it to date rocks or fossils, my presentation's going nuts. Right, so this can be used to date a rock or a fossil. Carbon-14, what we just started talking, or what we've been talking about, is going to be used for fossils and bones and wood that's up to 75,000 years old. So as we get any further in time, we're going to have to go to a different element. These are some half-lives of some other elements, just to kind of give you a reference that it's not just 5,730 years. I mean, right here we've got 4.5 billion years, 713 million years. This is just 1,600 years. So the amount of carbon remains constant throughout the organism's life. So we know the amount we start with. By knowing the end, we can work our way back. So if I know how much you started with, and I find X amount, however many years later, I can work my way back because I know where you started. I know how much carbon you began with. All right, so this is a graph that's something I would definitely have in my notes. I would draw this picture out or whatever, because on EOGs, they like to pull graphs in as well. What you have to understand with this graph is this over here, we've got 100%. Okay, this is 100% of the carbon-14. All right, that's what we start with right now today. When we divide in half, we're at 50%. Okay, that's one half-life. We've gone through one half-life. We divide in half again, that's 25%, 2.5 grams, so we're moving our way down. That's 2 half-lives. If I divide in half again, okay, I've gone through 3 half-lives. All right, and so on. So you may see it on a test or a quiz, you might see it on the EOG, where they use a graph to have you also show and understand half-life, okay? Parent and daughter material in terms of half-life. So this is something that I don't want it to be confusing. It's kind of easy to think about. But we have parent material and daughter material. Parent material is the original element. Okay, parent material is the original element. So I start off with element A. Okay, that's the parent material. The percentage of decay, as it decays, so we go by comparing the percentage of the parent. As it starts to break down, I form this daughter element, this decay element, which is the daughter, which we'll say is B. Okay, so as A decreases, B will then increase. So the age of the rock can be calculated. The ratio of the two atom types is a direct function of its age, because when the rock was formed, it had all parent atoms and no daughters. So when it formed, it had all the parents. And as it broke down, as elements start to break down, and we'll get to this in chemistry, but as we break elements down, we start to move throughout the periodic table. Okay, so we start to actually change that element. And this is where, as the parent element starts to decrease, the daughter will start to increase. So if I have a parent element of 100%, and I divide that, and I go through a half-life, I'm at 50%, which means my daughter is now at 50%. Do you see what I'm saying? And we're going to, so as the A is going down percentage-wise, the daughter is going to be going up percentage-wise. This is a way to look at it, trying to give you a visual. So we start off with, this is the parent, okay, parent playing tennis, whatever. Okay, as the parent starts to divide in half, all right, so we divide this here, we start to bring the daughter element into place. Okay, so mom went from 100% to 50%. Okay, so we know this is 100% over here. We know that this isn't quite 100%. So I couldn't give you the percentage, but we'll go 50% here, 25, 12.5. Okay, so as we go for parent, we have the daughter element plus the parent element is going to have to equal 100. So here we've got 100 and 0. Here we're going to have 50, 50. Here we're going to have 25, 75, and so on. Okay, that's what you want to be thinking about as we go from parent breaking down, daughter is increasing. Okay. Calculating half-life. So we're going to practice some half-life problems. We're going to do this in class as well. How old would a fossil be if it had only 1/8 of its original carbon-14 content? Remember, carbon-14 takes 5,730 years to divide in half. Sorry, my phone just went off because, well, that would be what happens. Okay, so we have carbon-14 taking 5,730 years to divide in half. Okay, so we always want to, and this is a chart way. Some of you who can figure it out algebraically, knock yourself out. Some of you who are more of a visual person, this is where you can sort of keep track of where you're at. I always set my time, and then I put amount. Time is always times 0, so don't go anything beyond that. Amount is 100%, all right, which is just 1. So as we start breaking down, I'm going to add my half-life on this side, and I'm going to divide by 2 on this side. And so that's all I'm doing. When I get to an eighth, when it asks how old would a fossil be, it's going to be 5,790 years. 17,190 years. I can talk. All right, so problem 1. The half-life of radon-222 is 3.8 days. How much of a 100-gram sample is left after 15.2 days? So we start off at time 0. We have 100 grams. Okay, we're going to add our half-life. That looks like a multiplication, but I'm writing sideways. We're going to add half-life over here, and we're going to divide by 2 over here. So I'm going 3.8. I'm going to keep adding 3.8 until I get to my total amount of time. Over here, so once I've gotten to 15.2, all I have to do on this side is continue to divide by 2 until I get to where it equals 15.2. All right, problem number 2. Carbon-14 has a half-life of 5,730 years. If a sample contains 70 grams, how much is left after 17,190 years? Same thing. Start off over here. This is my time 0. This is my amount. It's given in the problem. All right, so this side is dividing by 2. This side, I'm adding my half-life. Okay, so I need to get to this number, so I go to this side, I go all the way down, so I get to that number, there I am. So all I gotta do is keep dividing by 2 until it comes out. All right, problem number 3, how much of a 500-gram sample of potassium-42 is left after 62 hours? The half-life of potassium-42 is 12.4 hours. Now this time, I'm not gonna solve this with you. You're going to solve this and you're going to go over this as a warm-up in class, okay? I've set up the chart. I've also taken it down because it does say 62 hours, so I put your 62 hours in, times 0, 500. I've given you the correct amount of spaces. You just are going to have to go through and figure out the math. If you have any questions, please make sure you see your teacher, and I hope this makes sense, and you'll be getting extra work on this in class.